Hello students, in the last class we learnt about the mechanism of SN1 and SN2. In this class let us learn about some chemical reactions of haloalkanes and haloarenes. Let us see the dehydrohalogenation of haloalkanes. That is the second type of chemical reactions of the haloalkanes. The name itself indicates that DE is nothing but removal of, DE indicates the removal of hydro means hydrogen and halogen. That is, the name itself indicates that there is a removal of hydrogen and halogen. So that reactions are generally to be called as dehydrohalogenation. Let us see the haloalkane, that is R, CH, and it is H. So CH2 and it is halogen. So halogen attached carbon is to be called as alpha carbon, and the next adjacent carbon is to be called as beta carbon. So there is an elimination of halogen along with the hydrogens present at the beta position. That is, the HX is to be eliminated from the haloalkane by treating it with the alcoholic potassium hydroxide. That is, KOH is to be dissolved in the alcohol. That is, when haloalkane treated with alcoholic potassium hydroxide, it undergoes dehydrohalogenation. That is, the removal of hydrogen along with the halogen. So it gives the product, that is R and CH. So this bond is shifted towards the carbon and halogen is eliminated. So it gives CH double bond and it is CH2, plus the byproducts are, that is, potassium combines with the halogen, so it gives KX, plus hydrogen combines with the OH, so it gives H2O. That is, when haloalkanes with beta hydrogen atom, very important point, when the haloalkanes with beta hydrogen atom on heating with the alcoholic solution of potassium hydroxide or alcoholic solution of an alkali, so we can take sodium hydroxide instead of potassium hydroxide, undergo dehydrohalogenation and it gives the product, that is alkene. That is, the obtained product is to be called as alkene. That is, when haloalkanes undergoes dehydrohalogenation in the presence of alcoholic potassium hydroxide, it gives the product alkene. Let us take an example, that is dehydrohalogenation of ethyl bromide. That is, the formula for the ethyl bromide is CH3 CH2 and it is Br. So when ethyl bromide reacts with the potassium hydroxide, that is alcoholic potassium hydroxide, so it undergoes dehydrohalogenation, so it gives the product, that is CH2 double bond CH2 plus potassium combines with the halogen, so it gives KBr, plus hydrogen combines with the hydroxyl group, so it is H2O. That is, when ethyl bromide reacts with alcoholic potassium hydroxide, so it gives the product, that is ethene. Let us take the molecule which contains more than one beta hydrogen. In that case, the preferred product is to be identified by using Zaitsev rule, or it is also called as Zaitsev rule. That is, in dehydrohalogenation reactions, the preferred product is that alkene which has greater number of alkyl groups attached to the double bonded carbon atom. That is, greater alkyl groups attached to the double bonded carbon atoms are the major products in the dehydrohalogenation reactions. Let us take an example, that is 2-bromopentane. 2-bromopentane reacts with the alcoholic potassium hydroxide, that is 2-bromopentane. Pent means it contains 5 carbon atoms, 1, 2, 3, 4 and 5 carbon atoms, and second carbon contains halogen, so it is Br, and rest of the valencies are balanced by the hydrogens. So it is hydrogen and it is hydrogen, so it is CH2 and it is CH2 and it is CH3. Halogen attached carbon is to be called as alpha carbon and the adjacent carbon atoms are to be called as beta carbon. So in this molecule it contains 2 beta hydrogens, that is the name of the molecule is 2-bromopentane. In such a case, that is, it undergoes 2 types of dehydrohalogenation reactions. That is, first one, elimination of first hydrogen along with the halogen. So the obtained product is CH3, CH2, CH2 and CH double bond CH2. Let us take an elimination of second hydrogen along with the halogen. In that case, the obtained product is CH3, CH2 and CH double bond CH single bond CH3. That is, the first product is obtained by the elimination of first beta hydrogen along with the halogen, and in the second product, that is the elimination of second beta hydrogen along with the halogen. In such case, the major product of the dehydrohalogenation is the second product. So this is to be called as major product, because according to Zaitsev rule, during the dehydrohalogenation, the preferred product is that alkene which has greater or more number of alkyl groups on the double bonded carbon atoms. Here, this is the double bonded carbon atom. To this double bonded carbon atoms, it contains only one alkyl group. Only one alkyl group. But in the case of second molecule, it contains 2 alkyl groups. That is, it contains 2 alkyl groups. So the preferred product is 1, 2, 3, 4, 5. So it is to be called as pent and 2-ene. Pent 2-ene is the major product and pent 1-ene is minor product. That is, during the dehydrohalogenation, first observe the reactant molecule whether it contains only 1 beta hydrogen or 2 beta hydrogens. If it contains 1 beta hydrogen atom, there is no problem, that is easily eliminate hydrogen, that is beta hydrogen along with the halogen atom. If the molecule contains more than 1 beta hydrogens, in such a case follows Zaitsev rule. That is, during the dehydrohalogenation reaction, the preferred product is the alkene which has more number of alkyl groups attached to the double bonded carbon atoms. Next, move on to the reaction with the metals. That is how this haloalkanes reacts with the metals. Most of the organic chlorides or bromides and iodides readily reacts with the metals, and when it reacts with the metals it gives carbon metal bond, and such compounds are generally to be called as organometallic compounds. So organometallic compounds are the compounds which contains carbon metal bond. For example, when alkyl halide reacts with the magnesium powder in the presence of dry ether, that is alkyl halide is represented as Rx, and it is reacts with the magnesium powder in the presence of dry ether, so it gives an alkyl magnesium halide, that is the obtained product is RMgX. So it is to be called as alkyl and it is magnesium, alkyl magnesium, and X is nothing but halide, alkyl magnesium halide, and it is to be called as Grignard reagent. Very important point. In the examination they may ask how to prepare the Grignard reagent. That is, Grignard reagent is prepared by treating the haloalkane with magnesium powder in the presence of dry ether. Or in the examination they may ask what is the general formula for the Grignard reagent. That is, general formula for the Grignard reagent is RMgX. For example, let us take R is methyl group, that is methyl bromide reacts with the magnesium powder in the presence of dry ether, so the obtained organometallic compound is CH3MgBr. So it is to be called as methyl magnesium bromide. And when ethyl bromide, that is ethyl CH3 CH2Br, when ethyl bromide reacts with the magnesium in the presence of dry ether, magnesium powder in the presence of dry ether, so the obtained compound is to be represented as CH3 CH2MgBr. So it is to be called as ethyl magnesium bromide. That is, when haloalkanes reacts with the metals, that is magnesium powder in the presence of dry ether, it gives Grignard reagent, or it is also called as organometallic halides. In the Grignard reagent, the carbon magnesium bond is covalent but highly polar, that is carbon alkyl group and it is magnesium and halogen. So between the alkyl group and the magnesium there is a covalent bond, but it is highly polar in nature, with the carbon pulling the electrons from the electropositive magnesium. So the magnesium halogen bond is essentially ionic in nature, that is magnesium halogen bond is ionic in nature. That is, due to the pulling of electrons from the magnesium, the alkyl group has negative charge, and due to the electropositive nature of the magnesium it has positive charge, and due to the high electronegativity of halogen it has negative charge. That is, the alkyl group has partial negative charge, magnesium atoms having the partial positive charge, and halogen atom has negative charge because of the high electronegativity of halogen. Grignard reagents are highly reactive and react with any source of proton, that is they readily reacts with the any source of proton. That is, source of proton means, for example, let us take water molecule. Water is also a source of proton. That is, on ionization, it readily produces proton to give hydrocarbons. Even water, alcohol, amines are sufficiently acidic to convert them to the corresponding hydrocarbons. That is, when RMgX readily reacts with the water molecules, so it gives the product hydrocarbon. That is, there is an elimination of MgX, and the obtained product is RMgX plus and water molecules. So there is an elimination of Mg and it is OH along with the halogen. It is therefore necessary to avoid even traces of moisture from the Grignard reagent. On other hand, this could be considered as one of the method of converting the halides to hydrocarbons. Let us see how the haloalkanes reacts with the sodium metal. That is, when it reacts with the magnesium metal, it gives Grignard reagent. That is, obtained product is to be called as RMgX. When it reacts with the sodium metal, it gives hydrocarbons. That is, when haloalkanes reacts with the sodium metal, it gives hydrocarbons. Let us see how to prepare the hydrocarbons, or how the haloalkanes reacts with the sodium metal. That is, Rx is nothing but haloalkane. So the haloalkane reacts with the sodium metal in the presence of dry ether. So the obtained product has double the number of carbon atoms present in the halide. That is, Rx, sodium and Rx. That is, there is an elimination of halogens along with the sodium. So due to the valency of sodium 1, it is to be taken as 2 moles. That is, 2 moles of Na reacts with the 2 halogens, or it combines with the 2 halogens. It gives 2 moles of NaX, and the product is RR. That is, the number of carbon atoms present in the product is double in the number of carbon atoms in the alkyl halide. For example, let us take methyl chloride, CH3Cl. So when methyl chloride reacts with the sodium in the presence of dry ether, so it is 2 moles and it gives the product, and it is also 2 moles, and the product is CH3 single bond CH3. That is, CH3Cl plus sodium plus CH3Cl. So the 2 halogen atoms are eliminated along with the sodium. So it gives 2 moles of NaCl, sodium chloride. So these reactions are generally to be called as Wurtz reaction. That is, during the Wurtz reaction, the same type of alkyl halides reacts with the sodium in the presence of dry ether. It gives hydrocarbon, and the main point is the obtained hydrocarbon has double the number of carbon atoms present in the alkyl halide. So far we learnt about the chemical reactions of haloalkanes. Let us see the chemical reactions of haloarenes. Generally, aryl halides are extremely less reactive towards nucleophilic substitution reactions, but haloalkanes readily undergoes nucleophilic substitution reaction. But aryl halides are extremely less reactive towards the substitution reactions. This is because of the following reasons. Let us see one by one. That is, the first reason is the resonance effect. In the haloarenes, the lone pair of electrons on the halogen atom undergoes delocalization. That is, the resonance structure of the haloarene, that is, let us take chlorobenzene. So Cl has 8 electrons on the outermost shell. That is, the lone pair of electrons present on the halogen atom undergoes delocalization on the benzene ring. That is, these electrons are shifted towards the benzene ring and the carbon gets the 5 electrons, and the double bonded electrons present in the benzene ring is shifted to the next carbon atom. So the structure is to be represented as like this. That is double bond, and it is Cl, and Cl loses electrons, so it gets positive charge because the lone pair of electrons shifted towards the benzene ring, hence it gets the positive charge, and the double bonded electrons are shifted to the next carbon, so this carbon gets the negative charge, and the remaining double bonds are present on the same position, and again this negative charge undergoes delocalization, that is, it is shifted to the next carbon atom, and the double bonded electrons shifted to the next adjacent carbon atom, and the obtained resonance structure is to be written as, that is, this carbon gets the negative charge and it is double bond, and it is double bond, so it is double bond Cl, and there is a positive charge on the halogen. Next, the negative charge undergoes delocalization to the next carbon, and the double bonded electrons shifted to the next adjacent carbon atom. So the obtained resonance structure is, that is, double bond, and it is double bond, so it is negative charge, so it is double bond Cl and 2 lone pair of electrons and 1 positive charge. And finally, the negative charge shifted towards the double bonded carbon atom, and that double bonds are shifted to the halogen atom, and it gives the first structure, that is double bond, and it is double bond Cl and 3 lone pair of electrons. That is, this is to be called as first structure, and it is second structure, and it is to be called as third structure, and the first structure is similar to the last structure. In the resonance structures, there is a negative charge at the ortho positions and at the para positions. That is, the first structure and third structure has negative charge at ortho positions, and in the second structure has negative charge at the para positions, that is, negative charge at the para position. That is, CCl bond acquires a partial double bond character due to the resonance. As a result, the bond cleavage in haloarene is difficult than haloalkene. That is, in the haloalkene, it contains only carbon halogen single bond, but in the haloarenes there is a double bonds between the halogen and the carbon. Due to the presence of double bonds, it is difficult to break the bond. That is, it requires more energy in order to break the bond as compared to the haloalkanes. Hence, the haloalkanes readily undergoes nucleophilic substitution reaction, but aryl halides are less reactive towards nucleophilic substitution reaction. That is the first reason for the less reactivity of the aryl halides towards the nucleophilic substitution reaction is resonance effect. That is, and one more point is, and the next reason for the less reactivity of the aryl halides towards the nucleophilic substitution reaction is the difference in the hybridization of carbon atom in the CX bond. That is, in the haloalkanes, that is RCH2 and it is X, so it is to be called as alkyl halide, and in the case of aryl halides, that is halogen atom is attached to the aromatic ring, so it is X. Here halogen attached to sp3 hybridized carbon, and in the case of aryl halides, the halogen atom attached to the sp2 hybridized carbon. That is, in haloalkanes, the carbon atom attached to the halogen is sp3 hybridized, while in the case of haloarene, the carbon atom attached to the halogen is sp2 hybridized. The sp2 hybridized carbon with a greater s character is more electronegative and can hold the electron pair of CX bond more tightly than sp3 hybridized carbon in the haloalkane. Hence, the aryl halides are less reactive towards nucleophilic substitution reaction. And the next important point is the instability of phenyl cation. When aryl halides, that is CX, undergoes ionization, it gives a phenyl cation. That is, benzene ring has positive charge. So this is to be called as phenyl cation. So this phenyl cation is unstable. So it is not stable. Hence the aryl halides are very less reactive towards nucleophilic substitution reactions. That is, in the examination they may ask why aryl halides are less reactive towards the nucleophilic substitution reaction. In that case, there are 3 points. One is resonance effect, and second point is the difference in the hybridization of carbon atom in the CX bond, and the third point is instability of the phenyl cation. Next concept, that is replacement of halogen by hydroxyl group. For example, let us take chlorobenzene. When chlorobenzene can be converted into phenol, that is chlorobenzene to be converted into phenol by heating in sodium hydroxide solution, that is aqueous sodium hydroxide solution, at a temperature of 623 Kelvin and the pressure of 300 atmospheric pressure. That is, chlorobenzene reacts with the sodium hydroxide, that is aqueous sodium hydroxide, at a temperature 623 Kelvin and the pressure is 300 atmospheric pressure, and in the presence of an acid, that is the reaction takes place in the presence of an acid. So it gives the product, that is phenol, that is OH. So the obtained product is phenol and the reactant is chlorobenzene. That is conversion of chlorobenzene into phenol. So chlorobenzene to be converted into phenol by treating it with the aqueous sodium hydroxide in the presence of an acid at 623 Kelvin temperature and 300 atmospheric pressure. That is Cl is replaced by the hydroxyl group. So in the presence of an electron withdrawing group, that is electron withdrawing group is nitro group, at ortho and para positions increases the reactivity of haloarenes. That is the main point is, due to the presence of electron withdrawing groups in the haloarenes, the reactivity is increases, and if the electron donating groups are present at the haloarenes, the reactivity is decreases. Very important point. Due to the presence of electron withdrawing groups, due to the presence of electron withdrawing groups, the reactivity of haloarenes is increases. Let us see how the reactivity increases by the presence of electron withdrawing groups. That is, when chlorobenzene contains one electron withdrawing group at para position, that is NO2. So the reaction that is takes place, para nitrochlorobenzene reacts with the aqueous sodium hydroxide at temperature 443 Kelvin. So in the previous condition, that is in the absence of nitro group, chlorobenzene requires 623 Kelvin, but the para nitrochlorobenzene requires only 443 Kelvin temperature, and in the presence of an acid, so it gives the product, that is Cl gets replaced by the hydroxyl group, that is OH, para nitrophenol. So it is para nitrochlorobenzene and it is para nitrophenol. And with the increase in the number of electron withdrawing groups, with the increase in the electron withdrawing groups, that is one at ortho position and one nitro group at para position, and the reaction is, that is ortho para dinitrochlorobenzene reacts with the sodium hydroxide, aqueous sodium hydroxide, and the temperature is 368 Kelvin. That is, it requires less temperature than the one electron withdrawing group present in the chlorobenzene, and the reaction takes place in the presence of an acid. So it gives the product, that is two groups are eliminated and it is OH. So it is NO2 and it is NO2. And let us take an example which contains 3 electron withdrawing groups. 3 electron withdrawing groups. That is, 3 electron withdrawing groups are present at ortho and para position, NO2. So the reaction takes place. The reaction takes place even in the absence of sodium hydroxide. So here the temperature is just warm and in the presence of water molecules. So here there is an replacement of halogen atom by the hydroxyl group. So this hydroxyl group is obtained from the water molecules. So here it does not require any sodium hydroxide, NO2, and it is NO2. So the conclusion is, the number of electron withdrawing groups increases, the number of electron withdrawing groups increases, the reactivity of haloarenes increases. That is, in the presence of only one nitro group or one electron withdrawing group, the reaction takes place at high temperature. Greater the number of electron withdrawing group, the reaction takes place at very low temperature. That is, it does not require much temperature in order to carry out the chemical reaction. Next, let us discuss about the electrophilic substitution reactions of haloarenes. In the resonance structures, there is a negative charge at ortho position as well as at the para position. So, because of the presence of negative charge at ortho and para positions, because of the presence of negative charge at ortho and para positions, this haloarenes readily undergoes electrophilic substitution reaction. rather than nucleophilic substitution reactions. That is very important point. Haloarenes readily undergoes electrophilic substitution reactions rather than the nucleophilic substitution reactions, because in the resonance structures of the aryl halides there is an pi electron, that is electron cloud is more at ortho and para positions. Hence it attracts electron deficient species at ortho and para position. Hence these reactions are generally to be called as electrophilic substitution reactions. Let us see how these aryl halides undergoes electrophilic substitution reaction. In that first one, that is halogenation. That is when the chlorobenzene reacts with the chlorine in the presence of catalyst, that is anhydrous AlCl3. So here the electrophile generated is Cl plus, that is chlorine combines with the AlCl3, so it gives the product Cl plus plus of AlCl4 minus. So here the electrophile is Cl plus, it is electrophile. So this electrophile attacks at ortho as well as at the para positions. That is when chlorobenzene reacts with the chlorine in the presence of anhydrous AlCl3, so it gives the mixture of ortho dichlorobenzene and para dichlorobenzene, that is Cl attached at both the ortho positions as well as at the para position, and the obtained product, that is there is a replacement of hydrogens at ortho and para positions. That hydrogens combines with the extra Cl minus, it gives HCl. That is when chlorobenzene undergoes chlorination in the presence of anhydrous aluminum chloride, gives a mixture of ortho and para dichlorobenzene. Let us see how aryl halides undergoes nitration. Nitration means the haloarenes reacts with the mixture of HNO3 and H2SO4. It is to be called as nitrating mixture. That is when chlorobenzene reacts with the HNO3 in the presence of sulfuric acid, H2SO4. Here the electrophile is NO2, that is it is attached at ortho as well as at para position. Ortho as well as at the para position. It is Cl and it is NO2. That is when chlorobenzene reacts with the nitrating mixture, that is concentrated nitric acid and concentrated sulfuric acid, gives a mixture of ortho and para chloronitrobenzene. Ortho and para chloronitrobenzene. Next, let us see the sulfonation of chlorobenzene. Sulfonation means it reacts with the sulfuric acid. That is when chlorobenzene reacts with the H2SO4, that is concentrated sulfuric acid. So the number of moles is 2 moles, and it gives the product, that is electrophile SO3 attached at ortho as well as para position. that is Cl, and it is SO3, and there is one negative charge. Negative charge is neutralized by the hydrogen, so it is SO3H. And the next product is at para position, Cl, and it is SO3H. So here the electrophile is SO3, that is when chlorobenzene reacts with the concentrated sulfuric acid, it gives ortho and para chlorobenzene sulfonic acid. Ortho and para chloro, and it is benzene ring, chloro benzene, and next SO3H is to be represented as sulfonic acid. Sulfonic acid. Ortho and para chlorobenzene sulfonic acid. That is, during the nitration, NO2 group attached at the ortho and para position, and during the sulfonation, SO3H group attached at the ortho and para positions. And the next one, that is the reaction with the acetyl chlorides and acyl chlorides. First, let us take reaction with the methyl chloride. So this reaction is to be called as Friedel-Crafts alkylation. That is, when chlorobenzene reacts with the methyl chloride CH3Cl in the presence of a catalyst, that is anhydrous AlCl3, aluminum trichloride. So here the electrophile is methyl group. So the methyl group attached at ortho as well as at the para position, CH3 plus of, and the next product at the para position, CH3. That is, when chlorobenzene undergoes Friedel-Crafts alkylation in the presence of methyl chloride and anhydrous aluminum chloride, it gives ortho and para chlorotoluene. And next, let us see the acylation of chlorobenzene, that is chlorobenzene Cl reacts with the acetyl chloride, that is CH3 C double bond O Cl, acetyl chloride, or simply it is to be represented as CH3COCl in the presence of anhydrous AlCl3, aluminum trichloride. So the electrophile, that is carbonyl carbon, has positive charge, halogen has negative charge. So the electrophile part, that is CH3CO part, is attached at the ortho as well as at the para positions, that is Cl, and the positive charge on the carbonyl carbon. So attach the carbonyl carbon first, CO, and it is CH3, and at the para position, that is Cl and CO CH3. That is, when chlorobenzene reacts with the acetyl chloride in the presence of anhydrous AlCl3, it gives ortho and para chloroacetophenone. Ortho and para chloroacetophenone. Next, let us see the reaction of aryl halides with the metals. That is, the first one, Wurtz-Fittig reaction. That is, Wurtz reaction means which contains only alkyl halides. In the Wurtz-Fittig reaction, it contains both the aryl halides as well as alkyl halides. That is, ARX reacts with the sodium metal in the presence of alkyl halides. Alkyl halides. So there is an elimination of NaX, that is the product is 2 moles of NaX, and the main product is alkyl group attached to the benzene ring by replacing the halogen atom. So these reactions are generally to be called as Wurtz-Fittig reaction. For example, let us take chlorobenzene. When chlorobenzene reacts with the sodium in the presence of methyl chloride, CH3Cl, so there is an elimination of NaCl, and the reaction takes place in the presence of dry ether. So it gives the product, that is Cl replaced by the methyl group, plus the byproduct is 2 moles of NaCl. That is, when chlorobenzene reacts with the methyl chloride in the presence of sodium and dry ether, it gives toluene. So in the examination they may ask how to prepare the toluene from the chlorobenzene. So chlorobenzene reacts with the sodium and methyl chloride in the presence of dry ether, it produces toluene. So when the chlorobenzene reacts with the ethyl chloride, that is CH3, CH2Cl. So the obtained products is to be called as ethyl benzene, that is ethyl group attached to the benzene ring. Hence the obtained product is to be called as ethyl. So it is ethyl and benzene. Next reaction, that is Fittig's reaction. So in the Fittig's reaction, it contains only aryl halides. That is, chlorobenzene reacts with the sodium, that is 2 moles of chlorobenzene reacts with the sodium metal in the presence of dry ether. So it gives the product, that is 2 aromatic rings are joined through a single bond. Such compounds are generally to be called as biphenyl. So it is to be called as biphenyl. That is, bi is nothing but it contains 2 benzene rings. So the compound is to be called as biphenyl, and the byproduct is to be called as 2 moles of NaCl. Very important reaction. That is, when the chlorobenzene reacts with the sodium in the presence of dry ether, it gives biphenyl. So in the examination they may ask, explain Fittig's reaction, or how to prepare biphenyl from the chlorobenzene. That is, biphenyl is prepared by the reaction of chlorobenzene in the presence of sodium and dry ether.